So we're dealing with circle theorems today. And let's just start talking about circles. Well, you all know circles are round, and they're perfectly round, and they have a center. But did you know that circles have parts? So just like triangles and quadrilaterals, where first we took a look at the elements of the shape, let's take a look at the elements of a circle, right? So these are the elements or the properties or the parts of a circle. And I hope that everybody knows all of these things here. The circumference is the total distance around. You would also refer to circumference as perimeter. Right? That is the perimeter of a shape, but when we're dealing with a circle, we call it a circumference. Right? You will see over here, we have a chord. A chord is any line that touches two parts of the circumference. So once you have a line that touching the circumference at 2 points, that is called a chord. That chord, any chord, will separate the circle into segments. So you can see this here is a green segment, and this segment is called a minor segment. The smaller segments are minor segments. And then the big segment is this huge white segment here on the other side of the chord. And this huge white segment is your major segment. So you have your major segment and your minor segment, right? If a chord passes through the center of the circle, we call it a diameter. So the diameter is the only chord that will pass through the center of the circle. Yeah? And half of the diameter, right? So from the center of the circle to 1 point on the circumference is called the radius. Yeah, so the radius is half of the diameter, and that radius being half the diameter is a really important thing, right? You can actually write it down as like D is equal to 2 times R. Right? 1 diameter is equal to 2 radius, yeah? Or a radius is equal to D over 2, yeah? So our radius is half the diameter. If I take 2 radii and I put them like a pizza slice here, so from the center of the circle, I cut 2 radii, right? What I get here, this pizza slice here, is called a sector, yeah? And that sector has an arc. So an arc is just a piece of the circumference, and we can see that here. Now please do not mix up sector with segment. A segment can be formed by any chord. You just cut a chord through, you have a small segment, a large segment, a minor and a major, right? A sector has to be formed by 2 radii, like a piece of pizza. So it has to come from the center of the pizza, yeah, and go to the circumference. So 2 radius will give you a sector like a pizza, right? So we have the circumference, we have diameter, we have a radius. A tangent is a line that will be outside of the circle, but it will touch the circle at 1 single point only. That is super important. A tangent will only touch a circle at 1 single point. Yeah? And this whole tangent thing is really incredibly important. We know what an arc is. We know what a sector is. It's enclosed by 2 radii. We know what a chord is. We know what a segment is. So I think that covers all of the properties of a circle. So we have the properties of a circle, but there is one other very magical property that we need to talk about, and that is the magical number pi. Right? Remember, we did not invent this number. We discovered this number. Yeah, and it's a magical number, and it has to do with every single circle. Right? What we did was we realized that no matter how big or small a circle is, if I was to take the circumference of a circle and divide it by the diameter, right, I would get pi, which is 3.14, approximated to 3.14. Right? Then if I take this small circle and I take the circumference and divide it by the diameter, I would get 3.14. And no matter the size of the circle could be a planet. It could be Saturn or Jupiter. If you take the circumference of Jupiter and divide it by the diameter of Jupiter, you will get 3.14. Pi is this magical number, and it shows that all circles are related. Yeah? Now pi is also an irrational number. You see in here that this is the full length of pi. And did you know that there is actually a pi day? 3.14. Pi day is the 14th of March. Yeah? 14th of March, so pi day is coming up. And that's called pi day. And there are actually competitions across the world. There are competitions to see who could actually recite the most digits of pi. Yeah? So pi, it have people who could actually recite 20 something digits. Yeah? Pi is really a very important number. Now, we could see here that it's an irrational number. It never ends, which means that we can never know the true value of pi. We don't actually know what pi really is. We could just approximate it. For normal Csec questions, you are required to use pi as 3.14. Right? This little symbol here means approximately equal to, and I should have used that sign up here as well. But you could also, in some questions, they will say that pi approximates to 22 over 7. If you take your calculator, 22 divided by 7, you will get 3.1428. Well, that is not pi. Pi is 3.1415. But it's close enough. So a lot of times we will use this number here, and this is a rational number, it's a fraction. So it's very much rational, right? But pi is an irrational number. So that is why this 22 over 7, we just call it an approximation. So everybody understands the concept of pi, right? Yeah. So pi, the distance around the edge of a circle is the circumference. The distance across the circle through the center is the diameter, and the ratio of the circumference to the diameter of all circles is pi. Pi is 3.14159. Now, things are going to get heavy. Now, we are going to start to talk about those properties of a circle. Right? We have properties and we have angle theorems. Yeah? And this is what this entire class is going to be about. So let's jump straight into the deep end of the pool here. We have the first property of a circle. Right? And this property, you could imagine it to be a kind of common sense kind of thing. This is the center of the circle here. I have one radius coming out, and I have another radius coming out. First thing you have to understand is that all of the radius, no matter how much radius you draw, they will always be equal. Yeah? They will always be equal. So you have this radius here, CB, and you have the radius CA, and you're seeing that they're equal, right? So this property says that if I have two radii, they will form an isosceles triangle. So if I draw any two radii, because both of them are equal, means that if I was to join them with a chord from one point to the other at the base here, they will form an isosceles triangle. And I hope that makes sense. And remember the property of an isosceles triangle, that if it is that I was to draw another radii coming down to cut this chord at 90 degrees, right, then I would actually be cutting this chord, bisecting it in half. So this half would be equal to this half. Also, if these two radii here are at an angle y, right, y degrees, then if I draw this line here, I would actually be bisecting the isosceles triangle, which means that this angle will be half of y, and this angle will be another half of y. So a half and a half gives me y. Right? Also remember, in an isosceles triangle, the base angles are equal, so this angle will be equal to this angle. Now at the end of the day, everything that we learned here, we learned in triangles. This is actually the properties of the isosceles triangle, that you could bisect, and when you bisect it, it cuts it in half. We now have two right angle triangles, right, where the base is equal to the base on this side. This side here is equal to this side. This angle is equal to this angle, and this half y is equal to this half y. So these two triangles are said to be congruent. They are the same, right? So it might seem like a lot to take in, but just remember, you know all of this already. We looked at this when we looked at triangles. This is just basically the bisection of an isosceles triangle. So the real thing here is that any two radii will form an isosceles triangle. Yeah? And then all of the properties of an isosceles triangle come in after that. And you could see here that this diagram gives us a lot of information. I just spent the last 5 minutes explaining what you could easily see on the diagram. So this diagram is super important. So what I would suggest is that you guys make a sketch of this and make a sketch of the diagram and tell me when you're done. You're seeing that, right? So we have the two radii here, and those radii are equal. And if we join that, those, because it's an isosceles triangle, means the base angles will be equal. We have this angle y, the angle between the radii. If I draw another radii to bisect the triangles at 90 degrees, that means that I'll be cutting these two into two equal pieces, where this will be a half y and that will be a half y, right? Remember, the angles in a triangle add up to 180 degrees. So therefore, you could say algebraically here that x squared plus, no, sorry, not x squared, x degrees plus 90 degrees plus a half y will give me 180 degrees in this triangle here. Okay? Also, x plus y, this entire big angle here is y, will also be 180 degrees for the bigger triangle, right? We're talking about here the inscribed angle, right? Now, if we have 2 points on a circle, A and B, and you see we draw two chords, A going to C, and then B going to C. And this forms an angle X. And all 3 points are on the circumference, right? We say, and this is just a piece of language. This is not really a property, it's just a piece of language that we are going to use from now on. We say that this angle X is subtended by the arc AB. So when they say that an angle is subtended by an arc, this is what they mean. That we have the arc AB, and from the point AB, you draw two lines to another point there, and this angle here is the angle subtended by the arc. So just remember, like how when we were talking about triangles, how the opposite side, right? The length of the opposite side, it depends on this angle, the opposite angle. The bigger this angle is the bigger this side of the triangle is. Well, the same thing. If this arc was longer, or if this arc was much bigger, then the angle here would be bigger, right? So, in other words, what we are saying here is that it's just a piece of language here, that this angle is subtended by the minor arc AB. So Ariel, do you understand what it means when I say that an angle is subtended by an arc? Now we reach the first circle theorem. When you have an angle subtended by an arc, all of the inscribed angles that are subtended by the same arc are equal. So what does that mean? Well, I have the arc A to B, and I could draw this line here to meet C, and I could draw the line here, and I will get an angle X, right? But I didn't have to draw the lines there. I could have drawn the lines over here, and this is still going to be X. I could have drawn the lines over here, right? Where from A are coming here and from B are going here. But because this angle is subtended by this arc, this will also be X. All of these three angles are equal. So this first theorem is all inscribed angles subtended by the same arc are equal. Because I am such a great teacher, it means that you could just click this link here in your PDF, and it will actually take you to a GeoGebra link where you can actually play with it. Here you can see we have two 52-degree angles, and they are subtended by this arc here, right? So this arc here, this minor arc here. And you could see that if I take this, no matter where I put that on the circle, that 52 degrees stays the same. It does not change at all, because the distance of the arc doesn't change. So because the arc stays the same, means the angle will always stay the same, right? Now the only way to change that angle is to actually change the arc. If I was to change the arc, you could see the angle changing there, right? I can make the arc a small arc, and therefore I'll have a small angle. But no matter where I put that angle, it is subtended by the same arc, this arc here. So no matter where I put that angle, it will always be the same angle, no matter how I subtend the inscribed angle subtended by an arc. All inscribed angles subtended by the same arc will always be equal. That is the first theorem that we are learning here today. So this is still under Theorem 1. I'm just showing on you something, right? So this isn't a separate theorem or anything. This is still under Theorem 1. So you see how I have this arc here, and I draw two angles from that arc. One at the point C, which is X degrees, and then another angle at the point E, which is also X degrees. But guess what? C and E form another arc. And so therefore I would have these two angles here. The angle Y is subtended by the CE arc. You seeing that? Yeah. And the angle, this angle Y, is subtended by the CE arc. The angle at the center is twice the angle at the circumference if they are subtended by the same arc. So I have an arc AB here, right? And we saw that I could subtend an angle X from that arc, right? At the point D on the other side of the circle there. So you can see here that I could move this point D anywhere on the circle, and that angle x is not going to change, right? So what Theorem 2 is saying is that if I have an angle x subtended by an arc, you could see here that once we have an arc, the angle subtended at the circumference, and you have the angle subtended at the center, and the one at the center will be twice the one at the circumference, always. Yeah, and remember, this one at the circumference, I could move it anyhow I want, right? So if we click this GeoGebra link here, we'll go to another example here, where we could see that I have 55 degrees and 110. No matter where I move this, it will remain 55, and that will remain 110. Yeah, the only way to change it is to actually change the arc itself. So if I make the arc smaller, well, look, you see what's going on there, right? So this center angle will always be twice the angle at the circumference subtended by the same arc, right? So the angle at the center is twice the angle at the circumference if they are subtended by the same arc. Now moving on to Theorem 3, right? We have here an arc AB, but that arc is a semicircle. Yeah, you can see from the center here we have a angle 100. So this radii going straight out CB, and this radii going straight out CA. So we end up cut the circle in half. Angles subtended by a semicircle are always 90 degrees. Yeah, so if it is that you have a straight line, the angle at the center will be 180, which means that the angle subtended at the circumference will be a half of 180, which will be 90. So Theorem 3 is angles subtended by a semicircle are always 90 degrees, right? And we could actually look at it right here. We have a semicircle. And this is the arc we're dealing with here. This long arc semicircle. And we could take this 90 and fling it anywhere. And because it's all of these angles are subtended by the same arc, they will always be 90 degrees. It never will change. And remember, the angle at the center is twice 90, which is 180 degrees. Right? This here is also a part of Theorem 3, really. It's kind of the same thing as Theorem 2. It's not a new theorem, it's just something else, right? But remember how this angle here, 2x, is twice the angle x, right? Because this is the angle at the center, and this is the one at the circumference. Well, it is worked the other way around as well. So if I was to take this angle, this yellow angle in the center, and let's call it y, right? And I was to subtend an angle over here on this side. You see it, the angle coming from the same 2 points. This will be y, and this will be 2y. So this is not a new theorem. This is showing you that it is the same in both directions. If you're looking at this angle, x here will be the same. Sorry, this angle here will be twice. This 2x is twice x here, but then this reflex angle 2y will also be twice this angle on this side here, y. The first one where we have to find the angle x. Well, a couple of things I'm noticing, right? I'm noticing that this AB over here, right? And that AB is subtending this angle here, which is 100 degrees. It is also subtending this angle here. Now this 100 degrees, the angle at the center is twice the angle at the circumference. which means that this angle here is going to be 50 degrees. Everybody got that far? Nobody get that far?
So my answer was actually 50 degrees for x.
Yeah, but that is not x, no. You see, 50 degrees is this big angle here that is subtended by this arc. You see in that, Ariel?
Yeah.
Yeah, the point AB. So this big arc here, right, is, so this here is 50 degrees, right? Now, we could look at this small arc AE.
Excuse me. But I'll have to go and do something for my mom. I'll be back in like 2 minutes.
Okay, all right, no problem. Do your thing. Right? Now, we can see here the smaller arc AE, and that is where X is subtended by. You see in that area?
Yeah.
So we have to look for another angle that is subtended by AE. And if we look at it, this angle here, this here is subtended by AE, and
Yeah.
you get that? So therefore that green angle will be equal to X. You agree with that?
Yeah.
Right? So therefore, since this is 50, if you look at it, this here, this is not a radius, it's just a chord. This here, but these two chords are equal. Because these two chords are equal, means that this here is an isosceles triangle. You understand that?
Yeah.
So that means that this radius coming down here will be cutting that isosceles in half. Right? So that means that this angle gonna be 25, eh?
Yeah.
So if this angle is 25 and this angle is subtended by AE, then X is 25 degrees. You understand that?
Yeah.
Yeah, you're sure you understand it, right? You see it.
I see it, I understand it, but honestly, I didn't look at so much things in just one little.
Well, that is the thing. That is what circle theory is about. That is what circle theory is about. Circle theory, plenty of people afraid circle theory because you just had to know your work. It's a lot. And at the end of the day, you have to remember, one of the properties is understanding when an angle or how an angle is subtended by an arc. Yeah? So what you did was you found this 50 degrees and called that X. But no, this 50 degrees is subtended by the arc AB, and
Yeah.
so that can't be X, because X is subtended by the arc AE. Yeah, you seeing that?
Yeah.
Right? So we have to find another angle that is subtended by AE, and look, that angle is this, and And at the end of the day, don't worry, Ariel, because it's the first time you're doing circle theory, so I expect you to fail miserably, right? At the end of the day, remember, I will always give you harder questions than Csec, right? Now, we have to find the angle D and E over here. Well, we know that this is 224, right? We know that this is angles around a point. So we can immediately work out O. The angle O would be 360 degrees minus 224. 136. So the angle over here is 136. Anybody bother to work that out? Anybody saw that?
Yes, sir.
Alright, nice. So we got 136 here. We didn't even need to work out 136 here. We did not need to do that. But I'm just showing you, when it comes to circle theory, you have to be thorough, because there is always more than one way to do things. So remember how we were saying, it's this arc here, these 2 points here, right? These 2 points, so it's this arc over here. right? And remember what we were saying, how, well, okay, if this here is 136, then if I was to subtend an angle over here, this would be a half of 136, eh? Yeah, I agree with that, right?
Yeah.
Right. But I don't really care about none of that. The questioner asked me for none of that. But what I also know is that if this is 136, this here is a half of 136. Right? But if this is 224, then D is D coming from the same 2 points, eh? Yeah? So D is going to be a half of 224. Right? We saw that in after Theorem 3 with the yellow angle. Remember the yellow angle? Y in the middle, right? So because 224 is connected to these 2 points here, means that this angle D would be a half of 224. So 224 divided by 2 is 112. So this angle D over here is 112. Anybody got that for D? You know, we have the angle X at the point D subtended by the arc, and that angle at the center is 2x. The angle at the center is twice this angle here. But then we have this other reflex angle Y, and this is twice this angle Y here. Remember we were saying that?
Yeah.
Well, same thing here. You have to be able to see it. You have to take what you know and you have to be able to see it, right? So take a look at this, right? The angle at the center is twice the angle at the circumference, and it's the same thing for the reflex angle. The reflex angle on this side. So if you look at the question, look, the reflex angle is on this side, eh? And this is the point. We could take this as the point AB. This is the arc here. So we have the reflex angle on this side, which is 224, which will be twice the angle subtended by the same AB. You understand now, Shizzy?
Yes, sir.
Alright, Caitlin, you okay? Ariel, you okay? Yeah. So this is 112, right? Why are you not okay, Ariel?
It's not that I'm not okay now. It's just too much.
Yeah, well, we even start circle theory yet. We still have like 5 theorems to go. I tell you, this is a brain busting one, and I say,
So a lot of information.
Yeah, it is. We only do 3 theorems so far. So let me just take a little revision as the 3 theorems that we just did, right? If we look at it over here, right? We were talking about inscribed angles here. This is not a theorem. This is just us seeing what an inscribed angle looked like, subtended by an arc. Right? We see here that no matter where the angle is, if it's subtended by the same arc, it will always be equal. Right? We saw that. Yeah? This is really Theorem 1 where you have to know. Yeah? You don't have to worry about this one. Right? In fact, I'll go delete this one, so you don't have to study that one. Right? That one was just a little piece of thing. Right? So you have all of the angles subtended by the same arc. That's Theorem 1. Theorem 2, the angle at the center is twice the angle at the circumference, right? And then you could see here that the angle at the center is twice the angle at the circumference, and that is also true for the reflex angle going in the other direction. Yeah, and then Theorem 3 is angles in a semicircle will form 90 degrees. Yeah, those are the 3 theorems, right?
So I think, sorry, to cut you across.
No, of course you could cut me anytime. Yeah, I have 112 degrees here. Now if you look, these two lines are parallel, eh? So I have this line going so, parallel. This line going so, parallel. This is the transversal, eh? Yeah. And what did we learn about parallel lines and transversals? Well, we learned plenty things. We learned that these two D and E are co-interior, and co-interior will add up to 180 degrees, right? We also learned that this angle E will be equal to this angle on the other side here, right? Which is the alternate angle, if you could see the Z, this Z over here. So remember, you had to know all of these angle properties. Yeah? So because of that now, I could say, well, okay, E will be 180 minus 112, which is 68 degrees. Right? So you can see here that in this first one, we use this center angle to tell me that this angle is 50 degrees. We use the fact that is an isosceles to tell me that this small angle is 25 degrees, and therefore x will be 25 because they're both subtended by the arc AE. In this case, we have this big arc A, well not, it is the smaller arc AB, right? So because of that now, we saw the same thing. The angle at the center is twice the angle at the circumference. So that is how we get D. And then we actually use the parallel lines rule to get E. I mean, they gave us this 48 here, but they didn't give us G or O or anything. But this is a real important piece of information. This line is parallel to this line. So if these two lines are parallel, that means this 48 will be equal to this here is going to be 48. Yeah? This, why? Because alternating angles. Alternating angles are equal, right? So because this is 48, means that O will be 180 minus 48, which is 132. So now that we see here that O is 132 degrees, right? Now we can actually find G. So G will be 360 angles around a point. 360 minus 132 is equal to G is 228 degrees. So you can see here, we didn't really have to do that much circle theory. This one was more based on the parallel lines thing. Okay? Theorem 4 has to do with a cyclic quadrilateral. You know, a quadrilateral is two sides. Sorry, it's not two sides, four sides. Right? A quadrilateral is four sides. A cyclic quadrilateral is when you could have the four vertices on the circumference of a circle. So if you have a quadrilateral that is in such a way that you could draw a circle that would touch all four vertices, then that is a cyclic quadrilateral. Not all quadrilaterals can do this. Yeah? So you can't just take a rectangle and draw a circle around it and hope that all of the four vertices will touch. No. Right? There's only a special type of quadrilateral could do this, and that is a cyclic quadrilateral. So we could see here that we have the angle AB, right? Sorry, not the angle. We have these points here, A and C. If we look at the points here, A and C, right? From AC, we have this angle Y, which is at the circumference. And you can see we have the angle 2Y, twice as big at the center. Yeah. From AC, we see that we have the angle X on this side at the circumference. And we have the reflex angle 2X, twice as large at the center. And I hope everybody understands up to there. So Theorem 4 says that the opposite angles of a cyclic quadrilateral are supplementary. Right? That means that they add up to 180 degrees. Now it makes sense that X and Y would give you 180 degrees. Because if I take 2X and I add 2Y, you can see this here will obviously give me 360 degrees. Yeah. So at the center here, I have 360 degrees. That is 2X and 2Y. Which means that X plus Y, the opposite angles of a cyclic quadrilateral, are supplementary. They add up to 180 degrees. Everybody understand Theorem 4? Alright. So, Theorem 4. If you have a cyclic quadrilateral, the opposite angles will add up to 180. Now, conversely here, right, if it is you have a quadrilateral and you want to know if the quadrilateral is a cyclic quadrilateral, then just add up the opposite angles. And if the opposite angles add up to 180, well then you can confirm that it is a cyclic quadrilateral. Right? So that was Theorem 4. The opposite angles of a cyclic quadrilateral are supplementary. That is, they add up to 180. Theorem 5. The exterior angle of a cyclic quadrilateral is equal to its interior opposite angle. And we saw this. This isn't anything new. We actually saw this when we were doing quadrilaterals and we were doing triangles. We saw this, right? We saw it with triangles, right? The exterior, which is the exterior? This angle here, you see in this angle here, X? Well, this angle here is also equal to this opposite X. And I mean, it's obvious. It's obvious because X plus Y over here is 180 degrees. Because it's a straight line. We also know that X plus Y over here is 180 degrees. So obviously this will be X and this will be X. So Theorem 5, the exterior angles of a cyclic quadrilateral is equal to the interior opposite. That is this angle X here, which is exterior, outside of the quadrilateral, is the same as the opposite and interior angle. Yeah? The exterior angle of a cyclic quadrilateral is equal to its interior opposite angle. Right? Tell me when you're done it.
Done it.
You understand this one?
Yeah.
Alright.
Done it.
I have 2 donuts. I'll make him feel to eat donuts.
As a first, it's a good reminder, you know?
No, it's because everybody's saying done it, and every time somebody says done it, I just remember donut. It sounds like donut, so I'll get my hungry. I have 2 donuts. I'm waiting for 2 more.
2 donuts.
Alright. So I guess everybody done it, right? So that was Theorem 5. So remember Theorem 4 was the opposite angles of a cyclic quadrilateral are supplementary. Theorem 5 is the exterior angle of a cyclic quadrilateral is equal to the interior opposite. Remember, you had to be able to see all of this stuff, right? You can see I put a big arrow there for you to see it, right? And we have some questions here. Look at the quadrilateral, right? You're seeing the quadrilateral here, watch my mouse and a trace in it. You're seeing it here? That is the quadrilateral, right? You all seen it?
Yes, sir.
So if this is the quadrilateral here, right? This here is the exterior angle, which is 110. The theorem says that the exterior angle is equal to the interior opposite. So which is the interior opposite? Right? If this is 110, right? And this here is the point D. The opposite to the point D is the point B. So this point B is going to be 110. Right? If you notice, this point B is subtended by the arc AC. Yeah? So if B is 110, then X will be twice 110 because angles at the center are twice angles at the circumference. So X will be 220. So now we're moving on to Theorem 6. And don't worry, we're almost done. We're almost done. Right? Theorem 6 has to do with tangents. Remember, a tangent is a line outside the circle, and it will touch the circle, right? It will touch the circle at 90 degrees. Right? So Theorem 6 says that a tangent is perpendicular to the radius of a circle drawn to the point of contact. So if it is that I draw a tangent touching the circle at one point, and if it is that from that point I draw a radius to the center, that is going to be 90 degrees. Yeah? So a tangent is always 90 degrees to the radius that meets in it at that point. Right? Tell me when you're done it.
Done.
Right. Now I see in here a note that you will need Pythagoras theorem and trigonometry for these questions. We actually didn't do trigonometry yet. We're going to do trigonometry next. So maybe a couple of these questions you might need sine, cosine, and tan. So maybe a couple of these next questions you might not be able to do, but we will see. Right? So, oh yes, right. So that was Theorem 6, right? Theorem 6 had to do with tangents, and we saw that tangents meet at a point there, right? At 90 degrees. I only hear one done it, so let me wait for 2 more done it. For 3 more done it. Alright. Now Theorem 7. Any 2 tangents that are meeting at a point will be equal. Notice what is equal though. It's not the whole tangent is equal. You see the tangent touching the circle at this point. This tangent touching the circle at this point. These 2 tangents meeting at this point. So this point to this point here is equal from this point to this point. So these 2 sides here are equal. You see in the quadrilateral here, it's not necessarily a cyclic quadrilateral because it's not inside the circle. But you can see it here. If I draw a line from here to here, I will have an isosceles triangle. So the 2 tangents that meet at a point are equal from the point where they touch the circle to the point where they're meeting will be equal. Any 2 tangents meeting at an external point are equal in length. That is Theorem 7. Tell me when you're done it. So that was Theorem. So the 2 theorems on tangents. So you see we have 2 theorems on tangents. One says that a tangent is always perpendicular to the radius. The other says that 2 tangents meeting at a point will always be of equal length. Now we're talking about Theorem 8, and I believe this might be the last theorem. Right, so we're pretty much done. Yes, it is the last theorem, right? So we're talking about Theorem 8, and we see here that the angles between the tangent and a chord, right? So you're seeing not the radius but a chord. So we have a chord here. You could call this the chord AB. So we have the minor arc AB, right? And you know AB will subtend these angles Y. So these angles Y are subtended by a chord. Yeah. So we know that no matter where I move this angle, it'll always be angle Y, because they are subtended by this chord. Well, what they're saying here is that if it is that I have a tangent touching at the chord, yeah, not the radius but at a chord, then the angle between the chord and the tangent will be equal to the same angle that is subtended by that chord. So the angles between the tangent and a chord at a point of contact is equal to any angle subtended by the same chord in the alternate segment. So you can see here, remember, a chord is separate a circle into two segments. I have a small segment here, and on this side of the chord I have this large segment here. So this angle in this small minor segment is equal to the angles subtended by the same chord in the larger segment. Tell me when you're done. You will have in the Google Classroom here circle theorem. So you have the PDF that it's not even a PDF, it's a Google slide. So you can literally click all the links and things. Yeah. Not only that, but you know, you can click the links and it have these links here. But I want you to make sure for Tuesday you guys do all of these questions here. Cyclic quadrilaterals up until Theorem 6, right? Up until Theorem 6. Now, theorems after Theorem 6, those tangent ones, I still wait to try them. If you could try them, try them. But we didn't do trigonometry yet. But I don't think you might need trigonometry though. This one you need Pythagoras theorem, right? And I'm not sure. This one you might need trigonometry. So you know what? Up to Theorem 6 with the tangents, just do the questions up to there. But if you want to try the other questions, that's fine, right? When we come on Tuesday, we're going to correct all of these. So the questions that you're doing, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18 questions. So you have 18 questions. That's more than enough before we even reach Theorem 6. So you have 18 questions to do for Tuesday. And on Tuesday, what I will do is I will make a little worksheet with actual circle theory Csec questions, so you can see what a circle theory question looks like in the Csec exam.